Hello, everyone. Welcome back to day 3. And today it is my pleasure to introduce our first speaker, Peter Armitage. So thank you.
Thanks very much. Yeah, we're good. Okay, so yeah, great pleasure to be here. I hope this is a continuing series. Fantastic. You know, some of the talks outside of my area of expertise, but everybody is lots of really excellent science going on. So this is the third of the tutorial talks, and so I was asked to give a kind of a very broad background on some new class of experiments that both my group and a number of other groups are working on developing. It's a new technique. Two-dimensional coherent spectroscopy is itself not a new technique, as I'll tell you about, but applied to the terahertz domain, it is. And so one of the themes of my presentation this morning is that I think it's fair to say that the last, say, 10, 15, 20 years of condensed matter physics, there are many different material or physical systems that are characterized by what we might call quantum correlations, which are characterized imperfectly by conventional spectroscopic in particular, techniques, experimental techniques. And so what I'm going to be telling you about is our development of this new technique, terahertz 2D coherent spectroscopy. It's a pump probe technique. It's, if you will, it's actually like, and I'll make an analogy at points, to pulsed NMR, two-dimensional NMR, but not instead of using radio frequencies to manipulate nuclei, using terahertz pulses to manipulate electronic or magnetic degrees of freedom. It goes by different names in different contexts, right? So, you know, nothing is truly new under the sun, and so you can very often do things by combining different areas of expertise and knowledge. So nonlinear optics people would refer to this as four-wave mixing. In other contexts, it could be called photon echo. The 2D refers to two frequency dimensions, and so I'm going to tell you about that technique and applications of it. Unlike most nonlinear techniques, this is all happening in the terahertz regime, and there are small energies involved, a few millielectron volts, which corresponds to tens of degrees Kelvin. And so it's very much the energy scales that correspond to the kind of physics that many of us are interested in, things that happen, interesting material effects that happen at low temperatures. One of the advantages of this technique, I would say, unlike what happens in a lot of applications of ultra-fast techniques to quantum materials, is that the advantage of it is that I can tell you precisely what we're measuring. Right? That might sound like not a particular mark of distinction, but here it is. I can point to a particular response function, and I can tell my theorist friends what we're actually measuring, not something like something else, but really a particular response function. They may despair for calculating some third order response, but at least it's very precise what is actually being measured. Part of the analysis are very complicated, and if we use a technique that's complicated, we ought to have a good reason for doing it. But what I hope to convince you is that it's very powerful, and there's kind of really very novel information that you can get out. And I think we're really just at the beginning of seeing what we can do. Okay. Before I do that, let me thank various people that I've been very fortunate to work with, and in the interest of time, I won't mention all of them. People from my group over the years, various theoretical collaborators, people I've been fortunate to get materials from, more material collaborators, theory collaborators. The one person I will mention is my student Will Liang, who's right there, and he's right over there. And so I had a poster here 2 days ago, and he's the one kind of leading the charge on some of the work that we're doing on correlated metals now, which I think is going to be quite important. Okay. So first, kind of extended preamble. Any dynamic-driven system can have nonlinearities, and so materials and their interactions with light and matter is no different. Very often, nonlinearities in physical systems are a source of complication, right? So there's a reason we like linear response, or linear response for people who aren't used to thinking about this. The simplest version of linear response is Hooke's law. The force is equal to minus kx, right? So you apply a force, there's a deformation of a spring, which is linear in the force you apply. Ohm's law is another version of a linear response function. And there's a reason we like linear response. In linear response theory, particularly when we apply it to finite frequency, it's simplest, but it's also very, very powerful. There's very sophisticated mathematical relations that take you from, when you're talking about a complex response function, from the real part to the imaginary part. Very often we have reasonably simple models to understand the response of systems. Nonlinearities can be an interesting source of phenomena. Right? So this is the whole world of nonlinear optics, where they're taking this nonlinearities, which might be considered a bug, and turning it into a feature. Nonlinearities can be an interesting source of phenomena, but they can also be interesting probe of materials, and they can also give interesting information. And then they'd better be, because if we're going to do experiments, on a complicated materials with more complicated techniques, you better learn something that you couldn't learn otherwise. Otherwise, it's just kind of you're demonstrating your technical bravado. But really, if we're interested in materials physics, that's that's the end of the day. Very often, what we are going to understand systems is in terms of some kind of perturbative approach, the light-matter interaction. So the first term here is the linear response. You apply an electric field, for instance, and you get out a polarization. But then there are other higher order terms. Terms proportional to electric field squared and electric field to the third. They're probes of different things. And so second harmonic is perhaps the easiest to see. And it interestingly depends on certain symmetries being broken. And so you can kind of convince yourself, this is a cartoon of an anharmonic potential here. And so in nonlinear response, you need to have kind of some anharmonicities in the system. And here you imagine driving a little charged ball back and forth, if you will. And one of the things that you can see is, in equilibrium, the ball would sit at the minimum. But if you were to ask, what's the time average value once you start driving it, when it's subject to this, sitting in this anharmonic potential, the average value now becomes at some point far from the minimum. So there's a DC displacement that happens when you drive it with a field that goes like E squared, but that would only happen if it's asymmetric. Right? So nonlinearities, one of the things that they can be is a probe of symmetries. So the electric dipole radiation, as we're going to talk about what that actually means in a moment, is only possible in a nonlinear chi2 response. So we're going to use this language, chi1, chi2, chi3, depending upon how many orders of the electric field are there, that it's only possible in a system where you break inversion symmetry. And so we're going to use that at various points. But there are other possibilities and other different kinds of responses. And so there is this is the second harmonic generation here. So you have two photons that come in, if you will, and then one which gets emitted at double the driving frequency. And then there are various permutations of that. Another chi2 response would be difference frequency generation, where it's one frequency in, one big frequency, then smaller one, and then a smaller frequency emitted. Third harmonic generation, just a generalization of this, 1, 2, 3, and then one big one down. And then the one in particular that we're mostly going to be thinking about in this talk is called, again, in the nonlinear optics world, four-wave mixing. But this is kind of be the key to what we're thinking about. One important point that we have when we're thinking about nonlinear optics is we have to have in mind a slightly different idea about the interaction of lights with materials. So it's quite common, if I'm doing a sort of linear response optical experiment, I might have a source of light, and I have a detector of light, and I have a material in between, and the light goes from point A to point B, and I might use language like the photon was absorbed, or the light intensity was absorbed while it was going from the source to the detector. In nonlinear response, we don't use this language so much. What we want to think about is that we have a beam that comes in. It drives, let's say, charges in the material. Those charges oscillate. The charges themselves become a secondary source of radiation, and then they re-radiate. Right? So in linear response, the way this works is that re-radiated light is 180 degrees out of phase with the drive, and that looks like absorption. It is absorption. But in nonlinear response, we're going to think about driving a material. The charge is oscillating, or the magnetic spins being perturbed. And then there's going to be a re-radiated field that then we're going to detect in various fashions. And so that's, if you imagine this was a charged particle, that's what would be going on here. You'd be driving it, and it itself is a source of broadcast radiation, and we're sensitive to this in various ways. Okay? So optical nonlinearity is, of course, an old subject. This was nicely seen, or if you will, rather not seen, in the very first demonstration of second harmonic generation by Franken in the University of Michigan, 1961. The demonstration was made possible by the invention of the Ruby laser, which had created the required high intensities. This had just previously been a year earlier. And so in this experiment, what they did is they focused a Ruby laser with a wavelength of 694 nanometers down onto a piece of quartz. They sent the output light through a spectrometer, recording the spectrum on some piece of photographic paper, and it indicated the production of new light at 347 nanometers. And you can read what it says. The arrow at 3472 angstroms indicates the small but dense image produced by the second harmonic right here. And in fact, you don't see anything there because this is a famous story that the copy editor for PRL thought it was a speck on the photographic paper and removed it. So this seminal experiment, was, if you will, came into the world in this auspicious fashion. It was corrected in later versions. So now this is used routinely for technological applications. It's a huge field in itself, and it's become an important tool to characterize materials like semiconductors, right? And so now there are even demonstrations. This is second harmonic, but there are demonstrations in condensed matter systems of generating up to 100 harmonics. Right? So this can have rather important technological applications. Even more recently, there's been higher harmonic generation has been used to characterize various kinds of quantum materials that, again, we might say have hidden quantum mechanical correlations. And so one thing that was pointed out some years ago, and this was alluded to in Greg Feet's talk, that Chi2 nonlinear response is very sensitive to Berry curvature. And so I don't want to get into the details of this, but if you have a material which has interesting Berry curvature in the bands, and it's a material which breaks inversion symmetry, then the particular shape of the nonlinear response is a very diagnostic measure for what the Berry curvature is, right? It's not as direct, of course, as seeing like an integral of the Berry curvature, like you would get when you measure a quantized Chern number. But nevertheless, for systems where the Berry curvature integrals may not be quantized, this can be a very important diagnostic of it, and there's been interest in applying this. As I mentioned, Chi2 nonlinear response is sensitive to broken symmetries. And there can be very subtle symmetry breakings which are not picked up very well by conventional techniques. So in oxides, the nature of the symmetry breakings can very often be associated with oxygen motion, or primarily oxygen motion. And oxygen is not very sensitive, the conventional technique for structure, X-rays, not very sensitive to oxygen. And so in this particular paper, which I was fortunate to be involved with some years ago, we used 800 nanometer light looking at this high temperature superconductor, YBCO. And there's been a long-term debate about whether or not the pseudo gap, right? So underdoped cuprates have this interesting suppression in the density of states. And there's been a long-term debate whether or not this pseudo gap is a true broken symmetry state or some kind of crossover into some other phenomena which gaps spectral weight but is not a true broken symmetry. And so what was shown in this paper here is that there's actually a true symmetry breaking there. So you get no response, and then there's an onset here, which onsets something like an order parameter, and there's a line of phase transitions that persist in the phase diagram. Now, all of these things that I've just shown you here, they're second harmonic generation, Chi2. It's also using lasers, so the frequency ranges of the light are electron volts. So electron volt corresponds to about 10,000 degrees if you put it into temperature units. So the energy scales are far in excess of any kind of low energy degrees of freedom that we might be interested in. And so what I'm going to tell you about for the remainder of the talk is about a new technique where we use terahertz light to look at dynamics in various kinds of quantum materials. So 2D coherent spectroscopy is a nonlinear Chi3 technique with tremendous potential for various kinds of quantum materials. I give my conclusions in advance because when I invariably run out of time, you'll have seen them. I prepared too much. And I'll give you some examples of what we're doing with this. I'm going to talk about this in detail, but then give some examples of things which I think are particularly interesting. Spin systems with fractionalized spins, so fractionalized excitations. We'll talk about relaxation rates in disordered systems, what we call the Fermi glasses, and what we've termed marginal Fermi glass. And then tell you a little bit about, in fact, what Will is working on, and that's using this technique to look at nonlinearities interacting metals where you can get various interesting new kinds of information. Okay. So let's give you some kind of feeling for what this is about. So terahertz 2D coherent spectroscopy. So for starters here, imagine kind of as a cartoon that I have two weakly nonlinear oscillators. You can just imagine they're like charged masses on springs, or charged pendula, if you will. And I'm going to drive the system with two pulses, A and B. I'm going to drive it with A, and I'm going to drive it with B. And I'm going to imagine I can do an experiment with A and B together, or just A and just B. And then I'm going to look at the difference. So again, remember that we drive, let's say, charges, and they re-radiate. And so I can look at what is re-radiated when I use both pulses together, one pulse by itself, the other pulse by itself. And then kind of by definition, the residual is the nonlinear signal. Okay? And then I'm going to plot that nonlinear signal as a function of the pump frequency and the probe frequency out of the page in this fashion. Right? So if I had no nonlinearities, I'd get nothing. In fact, sometimes we get nothing. That's unfortunate. But what you can imagine in this particular case is, because these are weakly nonlinear oscillators, this is what I would get. I can a nonlinear oscillator has a feature that if you drive it, its frequency shifts a little bit. So you can imagine that I can drive it at the pump frequency and then probe it at the same frequency. And then if I pump it at the right frequency and probe it at the right frequencies, I see a response. Whereas if I pumped at the wrong frequency and then the inappropriate frequency and then probe another frequency, I would see nothing, right? And so in this fashion, you would see these two peaks that are kind of along the diagonal of the 2D spectrum in this fashion, 2D coherent spectroscopy. Very roughly speaking, the projection along the probe frequency, that's the linear response here. Okay? Projection is the linear response. Now imagine a situation where I go and I couple these two guys here. Now, if I was only doing linear response, if I had a good enough theory, what would I expect if I couple these weakly nonlinear oscillators? Well, what happens? Their frequencies shift a little bit. Maybe they broaden. They could become asymmetric. If I have a good enough theory, I could try to model that and kind of come up with some story about the nature of this coupling. But it's frequently the case I don't have good enough theory. What you can see happens in the nonlinear response, though, is you get these off-diagonal peaks. So it's not a matter of some subtleties or having a good enough theory. I mean, it's really just kind of an order one effect. I can go in, and physically it corresponds to nothing more than I can go in and shake one oscillator, and I can make the other one move. Right? And so in this fashion, I can resolve couplings between different kinds of excitations. Right? Now, another thing you can imagine doing is imagine a situation where maybe I have some dense spectrum of reasonably long-lived oscillators, nonlinear oscillators, but they all have similar frequencies. The linear response might be just this big blob here. And again, right, the projection is the linear response. And so what you find is along the pump and probe frequency direction is you would kind of get this ridge of spectral response. In linear response, you couldn't tell what the individual, perhaps long lifetime of each of these guys is, but you can go in and take, let's say, an anti-diagonal cut in this direction and reveal the inverse lifetime. Okay, so that's the basic idea, right? So you kind of understand. If you understood this, you understand the main gist of it. We're going to give. I'm just going to give. The duration of this is going to be lots of examples of this kind of theme over and over again. Yeah.
The color bar represents the nonlinear signal defined by
the what? Say it again.
Color.
The color.
Color represents a nonlinear signal defined.
Well, so here the nonlinear signal was just keeping track of these two. That's red, and this is green, and that's green. So that's the spectral response coming from that oscillator, and that's the spectral response coming from that oscillator. And right, so small pendulum is a higher frequency.
The linear part already subtracted.
The linear response subtracted. That's right. Yeah. So I've applied exactly. Yeah, exactly. So if the system, the linear response is subtracted, and a certain class of nonlinearities is also extracted. Right. So I use two pulses. And I use both pulses together, and then I use a pulse A by itself and B by itself, and then I subtract. So nonlinearities that come purely from A are subtracted. Nonlinearities that come purely from B are subtracted. But the cross nonlinearities are still there. And that provides a very sensitive way of doing this, right? Otherwise, you have to do things like use many different, you have to do many different experiments at different intensities and look to see what scales like e to the third and what scales like e squared. This is a much easier way of doing it. Okay, let me give one more kind of beginning example here, and then I'll ask if there are any other questions. And I should say, we didn't invent this. It's 2 Nobel Prizes have been given for two-dimensional spectroscopy doing NMR, right? So the Nobel Prize in Chemistry in '91 was for the invention of 2D NMR, and then Nobel Prize in 2002 was for doing a certain class of experiments in proteins in chemistry for using 2D NMR. In the Nobel Prize write-up in '91, it was said that 2D spectroscopy, quote, is looking at the skyline of a mountain range and then looking at the whole range in an aircraft from above. Right, so you can kind of get this analogy, right, when you're looking at this 2D plot. You look at the mountain range from the side and you don't have any idea how far it goes back. You look at it from above and you can see if it's a sharp ridge or a plateau. As an example of what people do in this world, in NMR, so this is frequency written in some units that I don't understand, chemical shift, but it doesn't matter. It's frequency and it's in the radio frequency range. And this is the NMR spectrum of a codeine molecule. And the details of this are not clear to me at all, but again, the projection, that's the linear response. This is really just exciting individual nuclei, right, with some particular frequency. And there's a diagonal line. And then you see here that some of these guys have off-diagonal peaks and others don't. And so the way this works is, right, it's very complicated, but what you can do is by kind of playing a game where you see which one is correlated with which other one and how intense the peaks are. There's dipolar coupling between spins. The intensity of these peaks corresponds to the strength of the dipolar coupling. And so from the height of these, you can work out how far spins are apart from each other. You know what frequency, each frequency corresponds to a particular, I mean, I'm just making this up, oxygen or hydrogen, but you understand the idea. And in so doing, work out the structure. So that's the kind of thing the Nobel Prize was given for in 2002. Nowadays, physical chemists are using this idea quite a lot, but not in NMR, but with lasers when they look at, say, molecular vibrations. So you can imagine some high frequency vibration. And one of the experiments that was done in recent years, kind of beautiful, looking at a protein which was folding. So you can imagine a big protein which has something here you can drive out here, something which is IR active, and another one there. And they're far apart from each other. And then the protein folds, and these two things come close to each other, and where they weren't before. And now these peaks grow on the off-diagonal regions where they weren't. And something about how fast they come together, you can extract the timescales. Okay, so we didn't invent this, but it's new to apply this to the terahertz range. So that's what experiments look like schematically. So I won't go into the details of this. Feel free to ask me questions.
Can I ask you a question? So why is it that you're looking at Chi-3 particularly?
Why Chi-3?
Yeah.
So I can get to that a little bit more. I don't have a good, a simple explanation for you. I mean, one reason is that Chi-2 is only allowed for systems which break inversion symmetry. So it's not a generic response. But it turns out that there are the kinds of things we're interested in, particularly when we start writing down things in a more formal language in terms of density matrices. The Chi-3 response is the kind of one which is most useful for us to kind of pull out various coherences which happen in the density matrix.
So that individual nonlinear component, the individual that you subtract out, that's also a Chi-3 that you subtract?
So yeah, so the question is about why aren't we looking at Chi-2? And in fact, we do get quite in the subtraction scheme we do have Chi-2, but generically it's not there. It could be there, and it's the spectrum actually turned out to be more complicated in many ways, right? So there's less of a intuitive description based on density matrices to make sense of it, but it's there. Yeah, and you'll see that in some of the plots that I'll show. Yeah.
So experimentally, you have the probe and the excite frequencies. You're tuning them individually, or each wave packet has some coverage over some frequency region?
Yeah. So in the cartoon version I gave, I wanted you to imagine I'm doing a series of experiments, one frequency, change the frequency, and kind of fill the 2D plot. In reality, what's done is we use these pulses, and you can see that's data, that's real data right there. And this is a pump and a probe, and we change the distance between these. And each one of these pulses, this is in picoseconds, and so it's about a picosecond wide. Inverse of a picosecond is a terahertz. And so it has all this Fourier content in it in the range that we're interested. And this is useful in some ways because we get a lot of frequencies at the same time, but also presents some complications. Okay, good. So that's what experiments look like. I don't want to get into the details of it, but maybe it gives you some feeling of the complexity. There's an ultrafast laser. A laser comes out, a number of beam splitters. What is important here is this laser is converted into terahertz pulses there and there are recombined, go through a sample, come to some particular detectors in this way, right? And so, yeah, ultra-fast laser, and I should actually have some real pictures of the real instrument, which particularly when it's running is beautiful with all the different colors. Okay, that's more data there. So this gives you a feeling for what we're doing. This is actually on phosphorus doped silicon, which I'll tell you a little bit about. That's again data there. These pulses, which are about a picosecond long, we slide them through each other, and this is, if you will, what the real data looks like. This is pulse A, right? So this is time versus time here, and pulse A is just not moving in time. We slide B through it. That's A, that's B, that's A, B together, and that's the residual there. And so this has all of the nonlinear response in it, all orders, actually. It's dominated by typically Chi3. There's Chi5 there. That's another generic response, but it's down by some large amount on the Chi3. And there could be Chi2 if the system, or Chi4 also, if the system breaks various symmetries. Okay, so what can we learn from this? So that's important. I convinced you that we can learn some things, but let's look at it in a little bit more detail. And so here, I'm going to show you some complicated stuff. I don't expect you to get all the details of it. I'm going to impress you with the complication, and you're going to see that it's a mess. But then what I hope to convince you is that we understand it, and that it's impossible to work through all the details. But what looks initially very messy is actually can be understood reasonably simply. So this is, imagine you have a classical electric field that looks like this. We're going to perform this procedure here of this subtraction where we use both pulses together minus a pulse by itself, minus the other one, right? And so we're calling this the nonlinear polarization, or it's some part of the nonlinear polarization. And I can take that and I can plug it into put this electric field into this nonlinear response in this particular fashion here. So if I factorize it, I will find that I get contributions to the nonlinear polarization, which go like 2 factors of the initial pulse and 1 of the second, or 1 of the first and 2 of the second. It's always 3 powers of the electric field there because it's a nonlinear pulse, if I'm talking about electric response. And so I can take that classical electric field, plug it in, and that's a big mess, right? You get all of these terms that come out. It's not quite as bad because it is a real response function, and so everything's coming in complex conjugate pairs in some fashion. But it's still complicated. And but then we can kind of group them, and we give them various names like third harmonic generation. This is what we're going to call the pump probe. That's another pump probe. This is we're going to call that a 2Q response. That's in the old literature called the free induction decay. That's another third harmonic response. That's called the non-rephasing response. This particular response here is called the rephasing response. In the language of spin echo or photon echo, which you might be familiar with from NMR, that's the photon echo or the spin echo term, this rephasing response. So that's like a Hahn echo, if you will. So one of the things that you notice when you look at it is maybe life isn't quite as bad as it would be otherwise, because there starts to be some kinds of patterns when I'm keeping track of the time dependence and the exponents. That if I think all the frequencies here omega, that's like a 3 omega signal, right? So it's oscillating at 3 omega. This one here is like omega minus omega plus omega. And you see the structure of this thing in front. It's like E star times E. E star is intensity. So it looks like, you can kind of think of this one as like the system absorbs some light with E star as the kind of counts the number of photons absorbed. And then it's measuring with E, so it's kind of the linear response on an excited state. Right? So there starts to be some kind of sense of that. This one here doesn't have the same kind of intuitive feeling, but is kind of important. Again, you might think that this is all a big mess, but this is one of the reasons why we plot things in this 2D map. So you had those frequencies, as I called them there, omega j and omega k. All right? And the reason why we plot things in these 2D maps, each of those different kinds of responses, in each of those responses encodes a different history of light interaction with a sample. They show up at different places in the 2D map. So this is some early data from Keith Nelson's group on this particular classical magnet. This is the time traces, which is very, very rich in time with these oscillations which go out very, very far in time. So the features are very sharp in frequency. And we can understand these different contributions. You'll see some of the same language here. Pump probe, non-rephasing, rephasing, 2Q, two quantum signal, SHG. And we can understand where they are by using what we call frequency vectors. So this rephasing is a negative omega j and two positive factors of omega k. And it appears there. This here is 2Q, so it corresponds to the system being excited twice and having two quanta, let's say two magnons excited, and then being de-excited. This response here corresponds to what we call the pump probe, and it corresponds to making a real population state, if you will, kind of absorbing some amount of energy in the system, and then measuring the system in the state after it's already excited, after there's a magnon, let's say in this case a magnon already there. And so that big complicated mess actually turns out not to be quite so bad. There was a question about Chi2 responses, and so Chi2 responses appear there. Chi2 has two powers of the field, which puts you there for a second harmonic response, and then there would be another one, the rectified signal, so the effective DC response would give you positive frequency there and then a negative frequency there. Yep.
This is an antiferromagnetic insulator.
That's an antiferromagnetic insulator. Yeah, it's a ferrimagnet actually. So it has a bunch of different magnon modes. And
so all the light matter coupling is through the magnetic field?
Yep. Yeah. So we can couple, that's a good point. So the question was, what's the light matter coupling? It's through the magnetic field, so it's magnetic dipole interaction. Yeah.
Why is the 2Q or the two magnon response at such a sharp energy? Because there should be many ways you can make two magnons.
Yeah, so it would be, because it happens through two successive excitations of, Kemp's question was why is it sharp and not a broad continuum? So it would be, if there was a couple, as there is sometimes, it would be a coupling of one photon where the two magnons were allowed because there's mixing into the one magnon sector. Okay, sorry, I'm making let me be a little more clear. There are spin systems where, let's say, spin is not a good quantum number. And so then the excited states are actually not, let's say, angular momentum eigenstates. I'm telling you something you already know, but I'm just clarifying, focusing the question. So in which case, you very often, you say, go in with flip one spin, and it has a coupling to one spin flip excited states, and then states which are mostly two spin flips, but have a little bit of coupling into one. In which case, then you excite this broad continuum. That's not the case here. We're imagining two successive excitations. Two photons are absorbed. So that's the simplest answer to your question. You would get a continuum if it was one photon making two magnons. Here we have two photons making two magnons. Yeah. This is the easier way to answer the second thing. Yeah. Okay, good. Okay, good. So I want to say a few more kind of maybe in the interest of time, I will just kind of say this because indeed I'm going to run out of time. The way we want to understand this in a more formal circumstance is in terms of density matrices. And so, putting it a little bit more formally, what this nonlinear response allows us to do is basically understand how density matrix evolves in time. And maybe I won't indeed explain all of this, but those people who are experts can just kind of realize that if you're unfamiliar, I was going to explain density matrices, but if I imagine like some two-level system in its ground state, what we do in this system, in these experiments where we have three successive pulses, is we basically excite the system, make a perturbation of the density matrix, time evolve it, make another excitation of the density matrix, and in each step here I'm kind of retaining some perturbation to the density matrix. Excite it again, time evolve it. And then the system radiates at some later time. So, oh crap. Okay, then I don't want to go back without having to play the whole thing again. But the point is, you have some expression like this in here, and you might be familiar with two-level systems, that there are different kinds of relaxation rates, right? There's a T1 time, there's a T2 time, and in a linear response, you only have access to the T2 time, and not in a fashion that allows you to discriminate between things like homogeneous and inhomogeneous broadening. Here you do. And so by doing experiments, different kinds of experiments where we perturb the density matrix in different fashion, we end up with this final perturbation of the density matrix, which depends on T1 and T2 in different ways. Right? And so this is the kind of thing that we can kind of do. Okay, good. Let me give you now some examples of what we're really trying to do with that. And so my first ideas about what to do with this kind of physics is, it's actually very similar, if you will, an analogy to that example I gave with the pendula, where you had this kind of dense axis with all of these pendula with slightly different frequencies where you couldn't make it out in linear response. And the idea here was to look at frustrated magnets, in particular spin liquid systems. And so spin liquid systems are systems where typically you might have some anti-ferro interaction on a lattice with a triangular motif, and if that spins up and this spins down, that third spin doesn't know what to do. A number of things can happen. Sometimes what happens is the transition temperature to some kind of nail state is just greatly suppressed. But there's a possibility that the true ground state is actually formed. The tendency towards spin anti-alignment basically manifests itself where you get this local singlet formation, where you kind of have this tendency towards spin anti-alignment by forming superposition of spin up, spin down by this kind of lozenge-shaped thing. And the true ground state is the massive many-body superposition of all the ways that you could kind of tile the lattice with these different singlets. Now, how to discover such a thing? Well, that's hard. One might hope to do some kind of spectroscopic experiment. But the problem is, if I say come in with a neutron or a photon, and I break that spin up, I can take that spin 0 object and I can turn it into a spin 1 excitation. But the spin 1 excitation is these two separate guys, and they can propagate separately from each other on the lattice. So we usually think of magnets as having spin 1 excitations, but here that spin 1 magnon, if you will, fractionalizes into two separate spin 1 half particles, and we call this a spin-on. The problem with measuring this spectroscopically is because there are two different excitations that can carry off energy and momentum, you get these very, very broad line widths. So there's a huge field of people interested in quantum spin liquids, myself included. But I have to say that very often I have neutron scatterers in the audience, and I hope not to offend them. The spectrum are very often underwhelming in spin liquids. I got a positive affirmation from Kemp on the front row. The spectrum are underwhelming. And so as somebody who makes their living doing spectroscopy, I want to see sharp peaks. And very often what you see in these spectrum are these big, broad blobs. And then, if you will, the cognitive dissonance is like, isn't it so interesting? The spectrum are so boring. This is an example of a material system, ytterbium, manganese, gallium 04, that I was involved with some years ago. These broad blobs here were taken as evidence for a spin-on continuum. So in this particular paper, where it was proposed that there was a spin-on Fermi surface, and the spin-on Fermi surface had particle hole excitations, and this gave this big broad continuum. The problem is this system is also incredibly disordered. There's an incredible amount of mixing between sites because some of these ions are the same size. And you may have an ordered state there, or a system wants to be an ordered state, but then this huge amount of disorder just scrambles the spectrum altogether. This is a very unsatisfying state of affairs where a system which is just completely disordered is indistinguishable from this very interesting, fancy quantum many-body superposition. Right? So another even simpler version of it is just an Ising chain in 2 dimensions. So if I imagine coming in again with a neutron or a photon, flipping a spin, I get a spin flip, but the elementary excitations of this state are these domain walls here. And so we've done a lot of work on terahertz spectroscopy in a particular material system, cobalt niobate, which is perhaps the best material example of this. And there what you see, this is the absorption spectrum as a function of frequency in the terahertz range. These big broad spectrum here where you have these peaks, but this corresponds to this 2 domain wall continuum. Again, you've excited the system and these 2 domain walls go out. There are many ways that you can make a k minus k pair, and so the spectrum are broad. So what to do? Well, this notion of pendula was what had occurred to me some years ago, and I was blathering for many years to theorists about this idea that I thought something could be done. And eventually, Yuan Wan, who's somebody who many of you know, who is a former student of my colleague Oleg Chernyshov, took me up on this, and we wrote this PRL some years ago where we did the simplest calculation for fractionalized spins, and that is the Ising chain in transverse field. So this here, that's the linear response, okay? So for the ideal case, this is real and imaginary parts, and this blob here corresponds to exciting the system with, again, making these 2 domain wall states, k equals 0. Okay? This is the 2D response. And you're now experts at reading this. This streak here through the fourth quadrant corresponds to making these k minus k pairs. This, you can take an anti-diagonal cut through that, and that's this sharp feature negative for a convention that we established in this paper here. But if this was this is kind of numerical error gives this finite width. But other than that, it would just be this kind of sheet of delta functions that we could measure the inverse with. Now, we did two other things in this paper. One of the things we did was just kind of by hand put in decay times to this. And so you can see what it does to the linear response. It takes this thing here and it kind of broadens it out a little bit on the edges. But if this was a real experiment, you would never believe me that I could extract out a lifetime from what the ideal curve would be to the little bit of broadening that happens on the edges. But comparing to this to that, it's just night and day, right? I can take the anti-diagonal cut and the width of this thing corresponds to the 2 spin-on lifetime. Now, this calculation here was done with no decays, but where all of the couplings were taken from some kind of disordered ensemble. And so in that case, again, what do you get? You know, you could never tell the difference between this and that. Again, there's some kind of broadening that happens on the edges, some kind of smearing of it. But this model is still integrable. You still get the streak of delta functions here, and the inverse width of the anti-diagonal cut. That's the lifetime of this thing. So that's what we want to do, okay? We are doing various kinds of experiments on magnet systems now. I don't have new data to show you on that, but this is what we're going in the future. It gives you a feeling, and I think a number of groups are interested in this. Let me show you some things in the remaining time about what we are doing, okay? What we have done. So first, I want to talk a little bit about this idea of the Fermi glass and interactions in it. So this is it's a long-standing question in the field about if I take an ensemble of localized charges in a disordered array and try to understand what's the nature of the low-lying excitations in this state. So imagine, as a physical realization, this is silicon, crystalline silicon, doped with phosphorus. So silicon has 4 neighboring bonds. Phosphorus is valence 5, and so there are 4 electrons which go into the bonds, 1 electron's left over, which goes into some kind of hydrogenic orbital, which many of you learned in your undergrad solid state class. So when the system is very dilute, you have this phosphorus, which is kind of held weakly, but still in a localized state nearby, and it doesn't talk to the other phosphoruses. If you make phosphorus concentrations larger and larger, then these orbitals start to overlap, and at some particular level of phosphorus, when you have about 1 phosphorus in 10 to the 5th silicons, you get some collectivization and you get a metal insulator transition. So early example of a quantum phase transition. But, and so this is data here from Tom Rosenbaum of resistivity versus temperature for a number of different phosphorus concentrations. And so that's the metal. It's some kind of, this we would also call a metal because it has finite resistivity. That's probably also in there, some metal. But then there's a transition to the insulating state. The insulating state is quite interesting. And one might ask the question in this about what is the importance of interactions in this system. There's a quote here that I liked from Anderson from 1970. As he writes, the Fermi liquid theorem is so he's talking about metals. He wants to make an analogy between what would happen in this localized ensemble of charges and what happens in a metal and what we refer to as a Fermi liquid. The Fermi liquid theorem is a rigorous consequence of the exclusion principle. It happens because the phase space available for real excitations decreases so rapidly as E squared or T squared. This is equally true for the localized case. At sufficiently low temperatures or frequencies, the non-interacting theory must be correct, even though the interactions are not particularly small or short range. The electrons can form a Fermi glass. And so Anderson's idea was, much like the notion of a Fermi liquid, even if interactions are not small, the consequence of having the Fermi surface is to basically normalize away those effects and put them in the kind of, if you will, virtual sector. And you normalize the effective parameters, but you don't change the fundamental structure of the theory. Right? So you still have, in a Fermi liquid, you still have electron-like quasi-particles there. They may have masses, which are very different. They have small scattering rates. They may have properties which are affected by the interactions themselves, but it's the parameters are affected, their magnitudes, but the parameters are still valid. Right? And so that's what Anderson's idea was here as well. And so our experiments using 2D terahertz on phosphorus-doped silicon indicate that this is not true. Okay, again, kind of in the interest of time, I will kind of skip through this. You've seen this plots before. And just to give you a kind of feeling for it. So this is a plot here of the 2D response for a particular sample of 39% doped phosphorus doped silicon. So it's 39% of the critical concentration to the metal insulator transition. You see a number of different features here, and I apologize, it's not so clear in this color plot. But now you're experts, and what you know is that the different places in the 2D color plot correspond to different physical processes. And in particular, I didn't discuss this, but one of the things that comes out is that there's believed in a system, which is a glass like this, that there's an emergent network of two-level systems. So it's really almost an exact analogy to what I was talking about. You have an emergent network of two-level systems. They're electric dipoles, but we can think of them as pseudospins. And then we can use all that language of magnetic resonance that I had employed earlier, even if they're just pseudospins. And so there are various kinds of, you see here, 1 over T1, 1 over T2. These anti-diagonal cuts here in the interpretation of these as two-level systems can be interpreted in this fashion. Even though the spectrums themselves are very broad, tens of milli-electron volts, these features are still reasonably narrow when you look at these anti-diagonal cuts. And so we can characterize them in various ways. One of the things you can do is kind of, if you will, take different cuts along these features, along the diagonal line, and then look at the rates of decay as a function of excitation energy. And yeah, it's a little bit, it unfortunately doesn't come out here very bright, but there are these lines here. This is for T1 and 1 over T1 and 1 over T2. And what you see in both cases is there's a linear dependence of 1 over T1 and 1 over T2 on the excitation energy with a slope very close to 1. And so the takeaway message from this is that if you could extrapolate these things down to the lowest frequency scales, there would be no low frequency regime which could be understood in terms of weakly interacting quasi-particles. In a Fermi liquid, things go like E squared. And so for low enough E squared is always smaller than E. But if it goes like linear, it's not. And an analogy with what's been discussed in some strongly interacting Fermi liquid-like systems, which are called, excuse me, I wrote this wrong. This is supposed to say, this doesn't say marginal, it's supposed to say a marginal Fermi glass. So an analogy with what has been discussed in marginal Fermi liquids, we term this state of matter the marginal Fermi glass. Okay.
Is there any special meaning for this dashed line?
That's just slope 1. This dashed line here?
Yeah.
Yeah, that's just slope 1. Right, so the point is that this thing is basically, that is also slope 1 there and just slightly below, right? So you can just see the coefficient. So it's linear in omega with a coefficient close to 1. Okay, I'm going to take just a few more minutes on this and then leave some time for questions. And yeah, so I don't really have time to go into this, but let me just say what we're doing here. And you might have been at Will's poster the other day and had a chance to talk to him about this. One of the themes of what I've told you about is that there are different kinds of rates of equilibration, right? So we can think very often about any physical system. We make some distortion to it, we change it, slightly excite it, and then we can watch it relax in time. Depending upon the nature of the perturbation, there are different kinds of relaxations that you can incur, and this tells you different things about the physics. And so the canonical case in a metal is, of course, the relaxation rate of current. You perturb a system, and you watch the rate that the Fermi surface recovers back to being centered around 0. This is what we measure in a conventional optical conductivity experiment. This is on a cuprate, a normal state of a cuprate. This is the conductivity versus frequency. And you see these curves here, which are kind of these Lorentzians. And the width of this curve, that is the rate of current relaxation. Or if the system has sufficient Fermi surface isotropy, it's the momentum is relaxing. So it's sensitive to a certain class of scatterings, the rate that a momentum leaves the electronic system. But there are other things that you could imagine happening as well. And I think in the interest of time, right? So that's the kind of conventional rate that momentum leaves. But one of the things we can imagine doing is using multiple pulses and exciting the system in various ways. It's interesting, it doesn't show up here. Did it show up here? Yeah, it doesn't play here on the screen like it plays here. This is supposed to have represented, it comes up here valid. It represents taking the Fermi surface basically and shifting it, shaking it back and forth and kind of leaving, if you will, charges here high and doing nothing there. That is, okay. So if I have if I've excited quasi-particles here on this side and that side, I can think of that as a superposition of, if you will, exciting all the way around, and if you will, exciting here, exciting there, and de-exciting there. And this corresponds to an A1G deformation of the Fermi surface, so kind of a uniform excitation. And this would correspond to the B1G. We might call that the quadrupolar or D-wave deformation. And one of the things that we're doing now, and I'm just going to skip through this because I'm totally out of time, is looking to see how these different rates relax. And so that's a very, very diagnostic for different kinds of scattering, right? So the rate that momentum relaxes, how does momentum be pulled out of the electronic system? That comes from scattering off impurities, Umklapp scattering, scattering off of phonons. The A1G, right, which is this uniform, that's the rate that energy leaves the electronic system. So Umklapp scattering doesn't do anything because it just one electron scatters off the other. They might exchange momentum, lose momentum, but they don't lose energy, right? The energy stays within the electronic system. So in the energy relaxation, that is sensitive to a different classes of scatterings. And so we've done a bunch of different stuff here, and you can learn about, we've looked at rutheniates and doped strontium titanate. That's an interesting case. There's an interesting kind of puzzle in doped strontium titanate that, even though it's a very low density metal, it shows T² dependence of the resistivity. You might think that's associated with electron-electron scattering, but the Fermi surface is very, very small. So too small to allow Umklapp. And people have thought that maybe it is some kind of funny phonon scattering because strontium titanate has weird phonons. And what our data shows is that that's not the case. Looked at some semimetals, which have very interesting phonon spectrums and interesting energy relaxation rates, and then also some interesting things on cuprates. And one of the takeaway messages on cuprates is that here what you find is the momentum relaxation rate in cuprates is that there's this famous Planckian dissipation, right? That the scattering rate goes linear in temperature with a coefficient close to 1. You find that the energy relaxation rate is in fact much, much smaller. And through what you can see in this analysis is that there's been over the years the thought that maybe the linear and T resistivity in the cuprates is due to coupling to some kind of bosonic system at high enough temperatures that you kind of have elastic scattering off those bosons. And what I think our data shows is that that's not an explanation. So I'm going to stop there. I'm out of time. I did say I would run out of time already, but you've already seen my conclusions in advance. And so I think I'll just stop there and take questions. So thank you.
Do I turn this on? Okay. Yeah, thanks, Peter, for a really nice and really informative talk. I guess I have a number of questions, but I'll just ask one first. So in the case of the spin systems, I guess what you showed us was that using the 2D spectroscopy, you could extract the intrinsic lifetime of the fundamental excitations of the system, which may be spin-ons. Yeah. But what I'm
just to be clear, of the two spin-on state.
Of the two spin-on state, yeah. So what I guess I'm wondering is, could you distinguish, using that, really distinguish spin-ons from the case of, say, magnons in a non-collinear magnet, or where you have anisotropies, where you have large magnon decays?
Yeah. So I think you can. So, in our paper, what we propose, so very often, as you well know, what people give as proof for spin liquid is say that you don't have ordering and the spectrum are broad. So that's not a particularly nice definitions for things. So our positive example, or our positive proof for spin liquid, would be where things are broad in the linear response, but can be narrow in the nonlinear response. So that's the idea, right? These sharp excitations in the nonlinear response, but broad in the linear response. So that generically should be taken as evidence for a multi-particle continua, with the caveat that the particles in the multi-particle continua are weakly interacting. So some spin liquid states are like, if you will, non-Fermi liquid spin liquids, right? So and that's an extra level of complexity. I think there just everything shows broad features. So if you have a system where the spin-ons can be considered weakly interacting, then I think we have a measure for it in those cases. But there are other examples where the spin-on degrees of freedom are themselves strongly interacting, and then I don't know. Yeah, I'm not sure we can do much with that. Yeah.
Can I ask maybe one ill-formed question? So neutron scatters now are often thinking about this classical quantum correspondence where quantum fluctuations show up as nonlinearities in the classical theory. And my ill-formed question is, it seems like, okay, you're looking at quantum fluctuations in terms of nonlinearities in the response function. Is there some connection there?
Yeah, so I didn't get the connection what you said about neutron scatters looking at nonlinearities.
So we're looking at these response functions and looking at, say, temperature dependencies, then modeling it with classical dynamics, but including nonlinearities.
Oh, got
which
it.
would have some correspondence with the quantum fluctuations.
So I only have an ill-formed answer. In general, nonlinear responses are much more sensitive to intrinsically quantum mechanical things, right? So we know that if I have a purely harmonic system, it essentially doesn't matter which way I do my classical physics or quantum physics, right? I can take a harmonic oscillator and I can quantize it, and then I can look at the correspondence principle in some classical limit, or I can look at the classical physics and then I can quantize my classical theory, and I get the same answer basically both ways. And that's really, I think, a pathology based on linear response. So in nonlinearities, then this thing starts to matter. And so I suspect that there is a route forward here from getting more diagnostic information. I think your intuition is right, but I don't have a better answer than that. Okay.
Peter, thank you for the great talk. I have two questions about the Fermi glass. So you extracted from 2D spectroscopy some relaxation rate, and it's almost proportional to the frequency with a coefficient of over 1. How does it compare with the Drude width in linear response?
So there's no Drude weight because it's an insulator.
Oh, this is already in the
It's on the insulating, so we're doing everything on the insulating side.
I see.
But this is the feature of this because the old prediction for so you can ask, well, what is the optical connectivity? There's still an optical connectivity, right? So it's an insulator, it's a DC insulator, but at finite frequencies you have these charges and they're localized and you can shake them around in some way and it dissipates energy, right? And so there are predictions first going back to Mott in the 50s and then later kind of refined by people like Efros and Shklovsky, who won the Buckley Prize for this in part, where there are various power laws in the predictions and the conductivity. But you can look, and I think it's debatable how well real materials follow those predictions. But nevertheless, what you see that comes out of that is that in that theory, though, it's basically still a weakly interacting theory. You have these dipolar excitations, and themselves are non-interacting. So you kind of put all the interactions in the dipole between the individual charges that make the dipole, and then you neglect all the interactions. So in our paper, we work with my collaborators Rahul Nandikishore and Sarang Gopalakrishnan, and we work out basically a kind of a theory which understands how these dipolar pairs interact with the other dipoles in the system. And that turns out to be interesting, and the marginalness of this is quite natural because dipolar interactions go like 1 over r to the third, which scales like volume, 1 over volume. And so one always finds, in general, another resonant pair that can be interacted with. That theory was actually first worked out by your colleague Leonid Levitov 30 years ago, how does a disordered ensemble of dipoles interact. I don't know what he had in mind when he was doing that, but that was an interesting theoretical issue.
And the particular rate, should I think of it as an energy relaxation rate or what kind of rate?
So we measured two things there. Right. We measured a T1 and T2. And so T1 is the energy, it's a population decay, but it's essentially energy. Okay. And then the other one is 1 over T2, and that's this dephasing rate. And they show differences. They show different at low temperatures, they both show that phenomenology. They show different temperature dependencies, and we don't have a theory for that.
Okay. Thank you.
Yep.
We have time for one very, very quick question.
This would be a quick follow-up on Liang's question. So let's say if you have a Fermi glass, silicon doped with phosphorus, for example, but with, say, different amounts of phosphorus, so different number of carriers, would you expect some kind of universality between these different samples of Fermi glass, or is there any signature in the measurement that can tell you this is a kind of unique feature of a Fermi glass? Other than measuring basically one sample with a...
Well, no, we measured many samples. I didn't show you. Okay, we measured all, and I just showed you a smattering of the data. So in our paper, we worked through the whole doping range all the way up to the metal insulator transition.
So basically my question is that what observation tells you that something is a Fermi glass, basically?
Well, so first of all, we know there are low energy degrees of freedom. So the notion of a glass here is really just by like analogy, if you will, to structural glasses. I have some object, an electron, which is localized, and it's in a disordered array, right? So at some level, the analogy doesn't have to go farther than that. There may be more explicit examples where, and more explicit analogies towards things like spin glasses, where there's long aging, the memory effects, all of those kinds of things that are found in glassy systems. Yeah. At this level, I just am saying it's an insulator because the resistance is diverging at low temperatures, and it's disordered, right? So at some level, it's that. Yeah.
Thank you. I'm gonna allow one more student question over here. Yeah. And if you have further questions, I saw a lot of hands, please do talk to the speaker during the break. Last question.
Yeah. For the last few slides, did you do optical pump terahertz probe, or is it just a time domain?
Say it again.
For the last few slides,
yep.
The optical conductivity,
yep.
Was it just time domain, or was it optically pumped?
So we're doing normal optical conductivity. And if I wanted to measure the current relaxation rate or the momentum relaxation rate, that's a parameter that comes out of the conventional linear response optical conductivity, if you will, the width of some kind of low frequency Drude response. But there are these other kinds of relaxation rates that roughly you can think of as perturbing the Fermi surface in different ways, heating it up everywhere around and watching how fast it loses energy, making a distortion, this B1G distortion, this kind of quadrupolar or D-wave distortion. Those are all done through these nonlinear experiments. Did that answer your question?
No, I guess wondering whether have you tried optically pump, like optical pump terahertz probe?
Oh, optical pump terahertz probe. I mean, there's a large literature of that, and there's some interesting experiments there. This program is really kind of, if you will, explicitly, despite interesting experiments there, is really kind of like trying to do things differently than that. Because when you, for the rest of the audience, there's a large literature of people where they pump with a laser, like say with a 1.5 eV laser, and then they look at the response of this excited state. 1.5 EV corresponds to 15,000 degrees in temperature units. So that's a huge energy scale. And so the implicit point of much of that experiment is you put in, let's say, one photon, which goes way up, and make this high energy electron hole pair. And then there's this kind of cascade of Auger processes, which make this kind of soup of hot stuff. But there are a lot of assumptions that come into that notion of how does this thermalization happen. And in these experiments, we don't have to worry about that. It's all low energy degrees of freedom. It's all Fermi surface. We're just taking the Fermi surface and we're moving it around in subtle ways, not some more violent process. So the answer is we didn't do it, but it's been done.
I see. Thank you.
Yeah. OK, thanks very much.
OK, let's thank the speaker. Our next speaker is Kemp Plum. Let's welcome him. Kemp, sorry.
Good.